Hello, everyone. Thank you for coming to this talk. Today, I will be talking about the generator-based design methodology in general, specifically focusing on some features of BAC 3.0, which we use here. So my name is Ayan Biswas. I am in my sixth and hopefully final year of PhD. I am co-advised by Professor Ela Dalon and Professor Vladimir Stojanovic. And in our group, we mostly focus on ultra high speed wireline designs. And we are also developing this Berkeley analog generator, which is the BAG framework. And we use that very extensively in our research. As I go through the slides, please feel free to just stop me and ask any questions if you have any, or we can also do questions at the end. Like I think I have slides for about 50 minutes or so, and then we can also like do questions towards the end. So yeah, this is the first motivation talk. So this is a picture that some of you may have seen before. It's kind of, we have it on all our back presentations, but this is like very briefly summarizing the main idea behind what we do in BAG, which is we have the circuit generator that takes in the performance specifications and the design methodology, like the intent of the designer, and it encodes the design process. And so by using the technology specific files and the different like verification and simulation tools, it can do a number of different iterations to come up with a final design that can be taped out. So in this talk, I will be focusing most on the BAC3 measurement features. I believe yesterday you folks have already heard a talk from Zhao Kai, who mentioned a lot about the layout features in BAC. So today I'm talking about the measurement features instead. And then I'll also very briefly mention how we have been using these nice features in BAG to design this current circuit that we are working on, which is a 160 Gbps energy transceiver for very short reach channels. I won't focus too much on the actual design because that deserves a presentation on its own. This is more of like using how we use certain features of BAG to design certain specific components for this circuit. That's what I will be talking about. So the contents, first I will briefly mention the development history of BAC3. Then I will, like I said before, I will focus on very specific measurement features and how they were very useful for developing our circuits. And I will go through these points one by one. And then finally, I will conclude my talk. So let's get started with the development. So the very first version of BAC3 was developed at BWRC like in late 2019 or late 2018, early 2019 by Eric Chang, who is the main developer of BAC2. Then there were a lot of subsequent development that happened at the startup called Blue Cheetah, co-founded by Eric, where I also interned for a time. We got out the open source release of BAC3 in around 2020. And at BWRC, we forked over a version of it. And then we have, at BWRC, we have a small team of developers, and we have been doing various addition of features, some code cleanup, documentation, etc. So this is a screenshot that you can see that I took like literally yesterday, right before I started making these slides. And the thing to note here is that the last commit here was done like 20 minutes, 28 minutes before I took this picture, which means that we are like very actively developing it and still adding new features. In fact, I will talk about actively still working on improving BAG and making it better for our use cases. So now let's talk more about the measurement API in BAC3. So one of the main reasons for switching to BAC3 instead of using the old BAC2 is to use this new measurement API. We had measurement capability in BAC2 as well. The problem was that it was like really difficult to use, which is why what ended up happening is most designers used it for layout generation, and then they did measurements in the normal way, which is just setting up like an ADXL test bench manually and going through all the flows. And nobody actually used BAG for doing the measurement because it was, like I said, like it was extremely difficult to use. in back 3, we greatly improved the API for interacting with all these different tools. And the API is also written in a way that we can support further tools in the future as they become necessary. And then what we do is we directly write and execute Spectre netlist from bag. So that means that we do not have to go through ADXL or Maestro anymore. And that significantly cuts down the runtime because we are just directly launching Spectre simulations and reading the results back. As a result, all these closed loop measurement and design scripts, which were possible in Back2 as well, but used to take really long to write and execute, have become much, much simpler to understand, easier to write, and faster to execute in Back3. So now let's talk about a few specific measurement features and see how those have been helpful for our circuit design. The first one I want to talk about is an automated design loop with characterization database and Sci-Fi optimization tools. So this is a feature that was added by one of the developers, Paul Kuon here, who is also in my year. And he has been working on the receiver for the 160 gigahertz transceiver that I mentioned earlier. So this was the use case for which he developed this design loop in bag. So the circuit that he was trying to design in particular is the track and hold circuit, which is at the beginning of the receiver front end, like right after the passive front end, like T coils and high pass filter. The track and hold is the first active component in the receiver. And there are a number of different parameters here which you can play with in order to improve the performance. So there's the tail device and the tail pull-up switch sizing, which affects gain, linearity, and ISI. There's the reset device sizing, which also affects ISI, and also common mode biasing, which affects once again all three. So there are like a number of different parameters that like layout parameters you can size in order to get your optimal performance. And so the trade-off can become really complex, and doing this analytically is not always a feasible approach because you also need to take into account layout parasitics. So the way we approach this is we convert it into an optimization problem. And this is how it works. Like we choose a certain design space. This is usually limited by like area considerations and feasible biasing in the process. And we have some target specs, which is how much gain we want to get out this stage. The pulse width, which obviously depends on like at what frequency we are operating this at and other things. And then once we have these specifications and the design space, we can use bag layout generators to generate the dart. And then we use the measurement processes that are available in order to characterize it. So this can be DC characterization, S parameter, like SP, noise, even things like PSS, etc. So you characterize the design the way you need to. And then we can keep iterating on this to create a huge characterization database. So we know that for every particular design in the design space, this is what the final design will, the final dart will look like, and this is the characterization features of that dart. Once we have the huge characterization database, we can interpolate the measurement results in order to find certain points like in between by optimization techniques to find the best possible dart that meets the target specs. So this is the entire design flow. Once again, this is something that we had a version of this working in Back2 as well, but nobody used it because it was so difficult to use. But now it is like very easily reusable. Like even though I showed this design loop for this particular circuit, it can be very easily reconfigured to work for other different types of circuits as well. And I will show another example of that in the next topic in my talk. So a few results from this design loops. Paul started out with 3,000 data points. There are like 64 device sizing, 4 bias points, 4 load cap, and 3 different corners. and he just launched it. In schematic simulation, it took 20 hours. Extractive simulation took a bit longer, of course, like probably around like a few days, but he was just running it in the background. And after you come back, once the simulation is over and you look at the plots, you can see that this is the gain from the track and hold stage for different values of C load. Here you have the V in common mode, the VI max, and the pulse width. And so based on these plots, you can now use the optimizer to pick out the best possible design across processes. This also helps him figure out what is the best biasing that he can do depending on the process corner. So this is one of the features I wanted to highlight. This is the design loop with characterization database and optimization that we have implemented in BAG 3. So the next one that I wish to talk about is how to integrate EM simulators into BAG as well. So previously we only had BAG interacting with Spectre in order to run circuit simulations. But then we did not really have the full EM support yet. Like we could draw inductors, but then we would just manually run EMX or HFSS, bring the S parameters over, and then run the Spectre simulations. What I wanted to do instead for my design is I wanted to also have the EM simulator be a part of the backflow. Some work related to this has been done previously. So this is a referencing a paper by Jeha from 2009, where for their 40 Gbps TX design, they had set up something similar to what I am going to describe, which is they start off with some guess of L1, like the inductors L1, L2, and the K, which is the coupling between two inductors. And then they actually use acetic, which is a flow that was developed by Professor Ali Niknejad from Berkeley. And it is kind of like a fast EM simulator that can give you pretty good results, close to EMX and HFSS results. And you can use that to find the inductor or transformer geometry based on your L1, L2, and K. Then they use layout parasitics and use certain algorithms in HSpice to come up with a model. So as you see in the picture on the right, for the spiral inductor, they could come up with the structure, like the model using ideal passive components. And then they run the simulation of their circuit, which was a CML buffer in this case, to check the overshoot and settling time, which is what they were trying to optimize. And then they keep refining it until it satisfies all their specifications. What we are doing is something similar, except that instead of acetic, we directly use EMX, and instead of HSpice, we are just running Spectre simulations to look at the final results and figuring out whether we need to change anything. So for implementing EM simulators in BAG, I created this new class called EM Sim Access. This one interface with electromagnetic simulators. So currently we have only support for EMX, but we can support other tools in the future as well. This gives us the S parameter files, which we can then directly instantiate in Spectre test benches using the import circuit element. And then we can, in fact, integrate this back into the design loop that I had mentioned before. So if you remember this picture from a few slides back, I told you that how once we generate a DAT, we characterize the DAT, and then we keep iterating here to create the full characterization database. But now if your DAT has a passive like inductor component, like maybe you are trying to do like an LC oscillator or something, then what you do is you split up these two stages into a few different substages. You first generate the DAT. So the layout generator will generate everything in the DAT, like including the transistors and the like power fill and everything. But it will delete the inductors because you don't want to extract the inductors. And in parallel, it will generate another layout which has only the inductors and T coils and whatever else you have, and also the associated routing, because that should also be taken into consideration during the EM simulation. But it will not generate like the transistors and MOMCAP and other things. So now this thing on the top now goes to the RC extraction tool to create the extracted file. in whatever format is appropriate for your PDK and your design tool. Um, the other one goes to the EM simulator, which is EMX in our case, and creates the S parameters. And finally, the two get combined in the Spectre test bench. So that has the extracted netlist and the S parameter files. And this is how you keep characterizing all the different designs that are available in your design space. And then the rest of the process happens as before. So we interpolate the measurement results, and then we optimize to find the design with the which means the target specs, in like by also consuming like minimum power or whatever the design objective may be. Um, so yeah, that was my talk about like how we integrated EM simulators into BAG. Of course, you can also use these EM simulators without doing the full design flow. Like you can literally have a single design and you just run it through BAG, and it just gives you the extracted netlist and the S parameters. And then you can just do the test bench separately as well if you haven't already finished writing up the full design loop. So in general, the way we develop these design loops is that we would first write the measurement a class, which does all the measurement techniques necessary for a particular dart. And once we make sure that that is working, that is when we start working on putting together the full closed loop design. One important feature that is necessary for doing this flow is, as I mentioned, you need to be able to create different views of the layout, which is, like I said, here we have one version which doesn't have the inductors and then one version which does have the inductors, which directly brings me to my next point, which is generation of partial layouts. And this is necessary not only for EM, but also for accurate load estimation. So the point here is that if we are doing block level simulations, then in our test bench, we need to have some estimate of the loading that is going to come from future stages, and also any like long routing to like maybe clock routing that's coming from far away or something like that. So what we instead want to do is we still want to do a block level simulation, but we want to have this long layout routing and whatnot to be present while we are doing extraction. And so we want to generate the whole layout, but then we want to keep only the components that are necessary for this particular block. So let me show you some examples to explain what to more clearly explain what I'm trying to say. So let's say we are looking at the transmitter. Extracting and simulating the transmitter will take a really long time. So instead, what we do is, let's say I'm focused on testing one particular block. I want the layout generator to generate only that block, and maybe like just the next stage to take into account the loading. And I want it to have all the top level routing so I can still see the effect of the power grid and everything. But I do not generate any other instances. And the way I do it is in the layout generator, we can commit the instances. So every time we add an instance, we can either commit it to be true or false. And if it's a commit false, then it won't be generated in the final layout. And like I said before, inductors have to be always deleted before the RC extraction, because they have to go through EM simulation and be replaced by S parameters in the test bench. So let's look at a particular picture. This is the architecture of my transmitter. Once again, I won't go into full details about the transmitter architecture because that is a presentation in its own right. But just the part that I want you to focus on is that right over here, from the red blocks to the green blocks, there is a region where we are transitioning in the clock domain. So the clock is 10 gigahertz in for these red blocks, and 20 gigahertz for these green blocks. So the timing of the signals at this interface is a really crucial thing that we need to look out for. And so when I'm trying to simulate whether the clock interface is done correctly, I don't really need to have like these serializers in the beginning or the output stage in the end to be present in the simulation. So I just need to make a layout which has like everything in this portion over here. So this is the layout of this architecture. It's kind of done like, so left to right is top to bottom in this layout. So you see the 128 to 16 serializer is up here. Then the this 221 is the 16 to 8 over here. There are the 2821 muxes which are here, and they have some series shunt picking. And then there's the GM stages down here, which will add up in the coplanar waveguide and the T-coil, which are not shown in this layout. These elements over here, the current control delay line, the IDAC, these are the clocking network, which are not shown in this architecture picture. But like, this is just the data path. There's also the clocking network, which is integrated into the data path layout in the way shown over here. So like I said, if I want to test only the data interface over here, I want to be able to generate a layout which has only like this portion of the full circuit. And so this is what this new layout looks like. So if you compare with the previous picture, you can see that the inductors are gone, the RDAC, and then all these clock circuits are gone, the low speed serializers are gone, and I have only generated the blocks that are necessary, but I do keep all the global routing. So the routing, the parasitics from the routing is still taken into account while doing this simulation. And then I just excite it with ideal sinusoidal clocks, because I have removed the block which generates the 20 gigahertz clocks. So I give it all the ideal clocks, I give it the data inputs, and I can just look at the output data from this. Also, I need to put in the S parameters for the inductors, which have been removed over here. And yeah, this is just a plot. And once again, I won't talk too much about the full performance of it. But yeah, this is just showing like across 3 different corners. Um, and then this one is the one UI delayed version of the previous one for implementing the FFE. But in this way, I can verify the timing at the clock crossing interface by doing a partial layout generation. Another example of the same thing shown over here. So this is testing whether the clock cells work correctly. So in this one, I want to provide the 20 gigahertz clocks as input, and I want to see whether the correct phases of the 10 gigahertz clocks are created and whether they have appropriate swing and everything. So in this picture, you can see that it kind of looks similar to the previous picture, except that the blocks which got generated are different. Like now, these 821 muxes, the 221 mux over here, those are gone. But instead, now we have this clock network cells. So there's the current DAC for generating the various currents for the current control delay line. There's the current control delay line and some muxes for the 10 gigahertz clock generation. There's also the divider for the low speed clock generation. And of course, all the top level routing still remains. And by running the simulation on that, now I can see like across 3 corners what the clock phases look like for the different frequencies. So yeah, this is where the partial layout generation helps us to simulate certain blocks by taking into account the top level routing effects. Okay, so the next thing I'm going to talk about is going to be very different from everything that I have said before. Like so far, we were only looking at spectre simulations or using S parameters from EM simulators in spectre simulations. Now we are going to switch tracks and talk about behavioral modeling. So as all of you are already aware, like having a behavioral model is good for running quick Verilog simulations to verify the overall logic of your circuit. So the reason that behavioral modeling was incorporated into BAC 3 is because we want to make sure that our behavioral model is really consistent with what our actual circuit is. Because what happens a lot of the times is, if model that models the entire TX or the entire RX, then often we can forget about some small things like maybe polarity or something. So maybe at some point we added some inverters to buffer a signal, and that reversed the polarity of the signal, but that did in the behavioral model, and so now the behavioral model and the actual circuit are performing drastically differently, and that can often result in further errors down the line. So instead of doing it like that, what we want to do instead is we want back to create the hierarchical model, the hierarchical behavioral model of our circuit whenever we generate a new circuit. So similar to having a layout generator and a schematic generator, we want to have a behavioral model generator. And the way it works is we write the models for the leaf cells, like the inverters and other logic gates, and maybe also the analog cells like a CS amplifier or whatever else you have in your design. And then we allow back to construct the hierarchical model of the top level cells. So every time we do certain changes in the schematic and the layout, a back will automatically generate a new behavioral model that exactly matches the circuit that we have. We have also found that we don't even need to provide models for memory elements, like the one that is constructed structurally from the leaf cell elements also work correctly once we run the Verilog sim. And like I mentioned before, we obviously do not want to model the top level cells because that will defeat the purpose of doing this exercise, because once again, we are trying to like really make sure that our model matches the small circuit changes that we do in our design. One interesting thing that comes out of this is we need to make sure our schematic hierarchy follows the modeling hierarchy, which can be different from the layout hierarchy. And the reason is illustrated in this simple example over here. So let's say we have just a very simple example, like two CS amplifiers cascaded one after the other. In the modeling world, you would want things to look something like this, because like there is no Verilog model for just a resistor on its own or just a transistor on its own, right? So when you are modeling, you want to model it as one CS amplifier and then another CS amplifier cascaded with that. However, if you think about the layout point of view, this is not the best way to break it up in the layout hierarchy, because if you make a cell which is like this, then in order to make sure that the layout is clean and the like at the edges it is still DRC clean when it is cascaded with some other block, we have to put some like boundaries on the edges. And now, even though you have placed another CS amplifier to its side, you still have the boundary, and so there's like a lot of area penalty, and this can result in a suboptimal area for this combined block. So instead, what you want to do in the layout hierarchy is you want to have like a resistor array, which creates an array of all the resistors. And so the space between every pair of resistors can be reduced because you don't have the boundary present there anymore. Similarly, you want to make a MOS array, which has the array of MOS. And then at the top level of the layout, you want to be able to route from the MOS to the resistor, and also obviously make sure that they are following some global pitch so that they align correctly. So in this case, you can see that from the layout point of view, this is about how you want the hierarchy to look like. But you cannot model this because there is no model for just a resistor array. So during modeling, you want to go like this. So here you can see that the schematic hierarchy now becomes the same as the modeling hierarchy. The layout hierarchy looks different. This is still fine in terms of LVS, because if you want to like LVS a single CSM, you can just create you can generate the layout from this structure and just say that we have an array of one, and then you LVS one CSM. And then if you want like 2, 3 or more CSMs cascaded, you just generate that many of them and you just run LVS, and you can still verify LVS, even though the layout and schematic hierarchy are different. But it is very important to make the schematic hierarchy and the modeling hierarchy match exactly, because that is how back constructs the hierarchical model of the top level cells, by looking at the schematic hierarchy. So let's talk about where this is useful. So one use cases for this is in the receiver side, because you may have some custom analog cells, and then you may have some synthesized digital on chip, and you want to be able to simulate the adaptive equalization by using the system Verilog models of the analog and the Verilog models of the digital. So that is one case where this becomes useful. But since I was designing the transmitter, I will give you an example from the transmitter where this was also very useful. So what I did is I created the full behavioral model of my TX, and I first generated the layout, I extracted it, and I simulated it across different process corners. In parallel, I also had the entire behavioral model of the transmitter in System Verilog. And a System Verilog also allows you to incorporate analog delay into the models. Like you can say that for an inverter, for example, I want the output to come out after a certain delay since the input got triggered. And then once I have these two models, what I do is I create the exact same transient test bench in both Spectre and Verilog so that I can directly compare the waveforms. So there is obviously some latency issue that you have to keep in mind because there is analog delay once again in the Spectre simulation. So you have to either make sure to include that analog delay in your behavioral models, or you can just say that, okay, like there will be some inherent latency in there. So we just start reading the signals after a certain delay. And as you can see in these pictures, this is the final output of the TX. This is before any optimization was done. So the swing is not very good. But the point is, this is just to verify that the timing is okay and the logic is okay. And yeah, if you like focus on the pattern, so this is a random pattern input and looking at the output of the TX. And if you look at this pattern here, it is the exact same pattern that showed up on the Spectre side, which means that not only my model matches the circuit correctly, but also like my digital logic in the TX was in fact correct. And this also helped me to figure out a lot of different bugs because I originally did have some bugs in my digital logic, and also the reset synchronization was not done correctly. And so like when I did the exact same experiment of doing the same transient test bench in Verilog and in Spectre, I was able to first find the bugs, fix them, and make sure that once again the waveforms that I'm getting from my Spectre test benches look the exact same as the waveforms that I got from the Verilog test benches. So yeah, this picture is showing how I verified the low speed serializers by going through this exact same exercise. So system Verilog modeling is something that did not exist in back 2 at all. So this is a new feature in back 3, and you can see that I have used it for testing various different blocks in my transmitter design. So maybe I'll just take a quick pause if there are any questions before going forward with the rest of my slides.
So what are the prerequisites for installing bag 3? How do I get started?
Okay. That is a great question. So it's mostly using all open source tools. There is only one closed source tool that we depend on. That is the open access API that you need to get from like the open access team. And then for the rest of that, we do have open source repositories. So as I mentioned earlier, yeah, so like you can either get the Blue Cheetah version, or you can get our version, which is in UCB Art. So this is a public repository. So if you just go on GitHub and search for UCB Art, you will be able to find it. We also have an open source repository set up in CDSFFMPT, which is it is like a fake FinFET process that's provided by Cadence, and we have Back3 set up in that. So you can look at that as reference for setting up a bag in your new process. Alternatively, if you can work out a deal with BWRC and give us access to the same process, then we can set up the primitives for you, which is actually the most difficult part of setting up bag in a new process. And once the primitives are set up, then you can just use the different features to make your own design. Regarding the other installation, there is a lot of C++ dependence because in back 3, most of the backend has been moved into C++ for better execution time. And so for that, you need like a lot of different C++ libraries to make sure things work out. Also, we need to be on Red Hat 7 or later, and then we need certain, yeah, 1 second, there are a lot of different dependencies, and I don't remember all of them off the top of my head, but yeah, we have like a list of them, and you need to have all of that to make this work.
Okay. Is there any part of it that you can still run without the OA dependency? Let's say you don't have access to the OA.
So without OA, you won't have layout generation, but okay. So here's the thing. In the C++ backend, there is a part of the C++ which depends on the OA and the part of the C++ which doesn't. But we haven't actually partitioned it very well, so it's not like you can compile one part without compiling the other part. But if we do end up doing that partition at some point, then yes, you will be able to compile only the part that's not dependent on OA and use that for like measurement things, but not for like actually creating any views that you can see in Virtuoso or anything. So yeah, like I guess to summarize, as of right now, it's not very easy to do that, but yeah, like if we get time and do manage to do the C++ partition, then in theory, it should be possible to do that.
One other question, you said that you read the PSF files. How do you read them? What library are you using, or have you written your own parser?
No, so there are some libraries that are available from Cadence. So there is there's a C++ parser, and there's also a Python parser. I believe it's called like PySRR. Yeah, that is the name. So SRR Python, that is the Python library, and I think that one is open source. There's also a C++ library which is not open source, and so we actually have support for both. Like we can make it switch between using the C++ parser and the Python parser. So yeah, like as long as you have access to the SRR Python, we can use that to parse Spectre PSF files.
I wasn't aware that it was open source.
I think the SRR Python, I mean, okay, it's not open source, but you do need to have access to Cadence tools like Virtuoso. And then if you ask them, you can also get the SRR Python very easily. Like the C++, that requires some more like license agreements, but the Python one, like if you have access to Virtuoso, you should be able to also get access to SRR Python.
I noticed you only have, usually if I get updates about changes, you just have one pull request that seems to just get different commits to it. Is there any plan to, I don't know, inform users about the changes you're making? Like maybe split up into multiple pull requests, or, you know,
So
release
that
it?
pull request is actually the new feature that I am going to talk about next, which I just created yesterday, and I did not want to merge it in before talking with the other developers first. So that's why it's not merged in yet, but like, it is my own pull request, and I can just merge it in whenever I want because I am the one who controls all the merging in this repos. But yeah, so yeah, we don't do like specific version releases. We just like whenever we find a new bug or we need a new feature, like one of the developers will add that feature and push it in, and then like if any particular user has requested us for that feature, we will just notify them. But in general, the advice we give people is you should just like git pull at least once every week to make sure that you are on the updated version. um, Okay, so maybe let me talk about this new feature that like I literally implemented yesterday. This was adding Verilog modules. So previously I was talking about system Verilog, but now like we also use Verilog for our designs for like creating some complex stimuli. And previously we did not have this, but then like there was one user who specifically requested this feature. So after my tape out was done, I decided to go ahead and implement this. So now, and once I merge this feature in, which is the pull request that you saw earlier, we can use Verilog modules either from the AHDL lib library or your own custom Verilog that you put in any custom library. You need to create a certain cell view info, and of course we will post examples about this in the open source bag repository that we have. But once you provide some cell view info, which is essentially just the lib name, cell name, the different ports, and the Verilog file for your custom module, or from HDL lib, that can just directly instantiate the module, inspector, netlist, and then you go ahead with simulation. Yeah, this was a feature I added like literally yesterday, and yeah, I will just make the other designers take a look at it before I merge it in. And so yeah, this is one of the new features. There are also like various different like cleanups that we are doing, because what happens is like, because we were like very much in tape out mode for the last 3 months, we ended up adding some few like local features here and there which haven't been like properly cleaned out and documented. So once once we get some time to recover and actually clean those up, we will also merge those in so that other people can use that as well. Yeah, so to conclude the talk, one of the questions that we get asked a lot is, is it worth it? Is it worth using bag, or whether it would have been better to do this manually? And I mean, of course, like I, being the lead bag developer right now, obviously I am extremely biased. But I can give you some points about why it does make sense in certain cases. So I think one of the main reasons why a lot of new users are put off from using bag is because it has a very, very steep learning curve. But once you cross that initial hill and then you start seeing the benefits of it, you really see like how much useful it can be. So let me just show you an example to illustrate this point. So this is the transmitter layout that I was showing you before, and this part, the part highlighted in blue, was entirely back generated. But whereas the blocks that are shown in white over here, which is the T-coil and this coplanar waveguide, so this is for the data and this is for the clock, these are not generated in back because the designer who was designing this just wanted to do this manually. Um, so this back generated instance, it took 2 weeks to write. This 2 weeks is not counting the time needed for doing the sub blocks. This 2 weeks is once I had all the sub blocks, how long it took me to write the top level layout and make sure that everything is still programmable, so that if like certain sub blocks change sizes or locations, everything else also automatically adjusts correctly and everything is still LVS DRC clean and the power grid is there and everything. So like, yeah, like doing that first instance of the top level of this part took me maybe like 2 or maybe slightly more than 2 weeks. But once I have the generator, recreating a new instance is now instantaneous. Like I want to maybe change the inductor like radius, I just in my like in my specifications file, I just increase the radius. I click run, and within 30 seconds, I have a new LBS DRC clean design ready to go. For these, however, it's not so easy because if like certain positions in this version changes, and now the coplanar waveguide has to come to a different point, because this has been done manually, it takes a lot of effort to resize it. So even if the original instance took maybe 1 week or so to get done, like make it like density clean and everything, for going through the iterations in order to make the performance good enough and make it route to the correct place, like every single like new instance takes close to 1 day of effort to make everything like pass all the DRC and LBS run sets again. So you can see that if you just go with these numbers, for the first 8 instances, manual layout is going to be faster than bag. But then for the subsequent 10, 20, 50 iterations, bag is just going to be so much significantly faster and like the better approach to take. Um, and this is just showing you the application in a single tape out. This is not even reuse across PDKs or reuse across designs of different performance specifications. This is literally in the same tape out, in the same instance, but doing some few like tweaks here and there to improve the performance. And you can see that even though I can very quickly regenerate a new instance of the transmitter to try to improve the performance, I still get limited by these manual layouts, and it will take me like 1 day to make the full change if I make one small change over here. And so you can see that like, yes, if you are going to make like one instance and it is going to be correct on the very first try, then yes, manual layout is definitely the way to go. But if you are going to be iterating, which is what happens in any real design, because we have to iterate to make sure we hit all the performance specs, then I mean, back seems to be like the very clear winner because of how easily we can create new instances. And of course, now that we have this, if we now move on to even an even faster node, or maybe we try to do another iteration of this in the future, which reuses some of these blocks, but not everything, we can very easily do that reuse. Like even in here for the low speed serializers, which is the 128 to 16 serializer that I showed before, that was just literally directly taken over from a previous step out that we had done in a completely different process for a different target speed. It was for like I think it was like 100 Gbps NRZ, whereas this one is 160 Gbps NRZ. So I took the generator and I just generated this new thing. So my low speed serializers were immediately done. And then I focused all my attention on designing the more high speed muxes and all the series shunt inductors and all that. So yeah, I mean, first instance is definitely much slower than doing it manually, but every subsequent instance like is just so much faster. And so yeah, like based on that, it does seem like it is worth it to use not only BAG but any other kind of generator based methodology. Like it might be Lego 2, which JDAT has been developing. It might be Anagen, which has been developed in Infineon. Like whatever generator you want to use, like it definitely makes sense to do a generator based design rather than a manual design, because even though the initial effort is extremely high, like every subsequent iteration becomes much easier. So yeah, that concludes my talk, but yeah, feel free to ask any questions.
So have you been using Lego 2 also?
Achilles, can you please come closer to the mic? Because we cannot hear you so well. I mean, the audience would like, or is it Curtis? Oh, thanks.
Oh, there's me. Did you use Lego 2 in your design here also?
No. I haven't used Lego 2 at all. Like I saw that about Lego 2 when I looked at the schedule for this bootcamp.
So basically, you're using this MOS space that Zalkai kind of were talking about yesterday.
Yeah.
Okay. So I have one question, but maybe I will be at the end. Let's like others give the opportunity to ask.
I have one question. Do you guys publish the primitives for Sky 130? Is there openly available?
Sorry, which one?
The bag primitives for Sky 130 technology?
So for Skywater 130, there were some primitives that are available like from Google directly, and those were created by Blue Cheetah. So that's not like our version. And the reason for that is because at BW, I don't know if maybe you know this already, but Skywater 130 has two different versions. There is the open source version, and there's also a closed source version. So at BWRC, we do have access to the closed source PDK, which means that we have updated our primitives to work for the closed source one. So we cannot really release it until Google releases it. So yeah, that's the thing.
Okay. And these are bag-free primitives, I guess. Not bag 2.
Yes. So like bag 3 primitives for the open source Skywater 130 are available if you go to Google's GitHub. But the closed source primitives, those we also have to keep closed source because we cannot release it until Google releases the PDK.
How much? I mean, you did a lot of bringing bag into C in order to accelerate, but the primitives, they should have stayed the same or has that
Yes,
changed as
yes.
well?
So when users write the generators, those are still in Python. The primitive implementation is also in Python, but the design framework has gone to C++. Like, for example, when I was doing this Verilog feature, I did have to write some C++ to make the netlister work. So also the netlister that I mentioned before, like we have an internal representation in BAG, and then BAG uses that to write the Spectre netlist and also the behavioral model. That entire netlister is in C++. So the backend has been moved to C++, but the front end, the part that the users see, that is still in Python.
Okay, but let's say the primitives, the configuration files, the YAML files. If you would have a version of BAG 2, could you easily copy them into BAG 3 and they work, or is there quite some difference?
It is. There are some changes that have happened, like even though maybe the class names are the same, the implementation has changed. So yeah, like it's kind of a code cleanup. Like when Back2 was done, we were not really following a lot of good software practices, but ever since then we have become better at it. And so yeah, like the signatures of different methods have changed. So yeah, like if you already have back2 primitives, it is definitely easier to write the back3 ones, but it still takes some effort.
I think I get it.
Yeah.
Thank you.
Question from my side. So you said you have the system Verilog for the behavioral models.
Yeah.
So now you're simulating the spectra, or do you have some mixed signal simulator interface?
We can do mix simulator, mix signal as well. We didn't do this for this particular tape out, but yes, that is definitely possible. So like I mentioned in the very beginning, the BAG API is now written in a way so that it is very easily to support new simulation tools. So even though we haven't supported AMS simulators yet, that shouldn't be very difficult to set up. But currently we have that done separately. So like in the use case that I did, I literally did a Spectre simulation, and in parallel, I did a Verilog simulation. And I was just checking the waveform at the end of that by running the same transient sim to make sure that they match up. But what you are describing should also be possible. It will once again, I guess that is like a new feature that may come up in the future, where we do integrate an AMS simulator into here and make sure that we can run mixed signal simulations. So we don't have it now, but yeah, that's like in the wish list for doing it in the future.
Question from me. You mentioned the high learning curve of Bag3. So whenever you have to onboard someone with using Bag3 in your laboratory, how do you usually approach it? Do you just have them fork Bag3 and have them do look at the examples, or do you have them start with, say, an older version like Bag2, which is, I think, simpler, or maybe Bag2 is more complicated still?
It kind of depends from user to user. Like we have had users who first learned Back2, and there is in fact an open source bootcamp that is available that I actually showed you all like 4 years ago when I went over to Infineon. But yeah, so that one is already available, and there are some users who went through that and then they learned Back3 as the incremental update from Back2. But then there are other users as well. So like Paul Kwon that I mentioned, who is now a Back3 developer, he learned Back3 in the beginning. Like he didn't even use Back2 before. And the way he learned it is, it was like a mix of reading through some code, some documentation, maybe trying out some simple examples. So you try to look at the inverter example. Another example that I think is very useful for making new users familiar with the programmability is you take a circuit which is implemented in NMOS, like maybe you take a strong arm with NMOS input, and you try to include some programmability in the generator so that now it can generate a PMOS input strong arm without writing a new generator, like just include the programmability in the old one, so that now you have a flag so that you can say whether I want an NMOS input or a PMOS input and generate that. So by doing the small examples, yeah, you start to learn it. And then depending on whether you want to become a bag user or a bag developer, like if you want to be an user, you just learn how to use the existing features. Whereas since Paul wanted to like develop his own features and add more to bag, he actually went on to become a developer. So yeah, I think like in general, just some Python background and maybe some background in C++, though you can learn that on the go if you need to. That is enough to get started with that.
So for Paul, how long did it take him to become a user, one, and two, to become a developer?
Um, Well, so I would have to ask him exactly how long it took. Like, so here's another thing. Like, you don't have to become an expert in every single thing, right? Like, you can, like, for doing the development work that he did, he only developed the design loop thing, like the closed loop design. So he probably doesn't know like the entire way of doing the layout primitives, but what he is more familiar with is the measurement setup and how to get all that working. But then like I, for example, know most of everything, but then there's also some point where I wouldn't understand any further, like so there's a lot of C++ geometry that's happening, and we actually did find a bug there, but I actually don't know how to fix it. So that's something that only Eric knows, who is the one who originally developed bag. So like my point is that you don't need to know like every single thing. Like maybe you first start off with the layout side, or maybe you just first start off with the measurement side, and you make sure that you can write in nice measurement scripts and design scripts using schematic designs. And then later you start learning the layout. So it's not like you have to learn the entire thing to start using it. You can learn it in parts. So I guess since you asked that question, maybe I should mention one more feature that is there in Back 3 that wasn't there in Back 2, is that in Back 3 you can run measurements on custom designs. So it's not necessary that you have to write like a layout generator and schematic generator and have a back generated dart in order to run measurements. You can literally take a dart that has been done manually or just like custom by someone else, like maybe a PDK provided pcell or whatever, and you can just take that. And so like you remember this cell view info I talked about for Verilog A, this also applies for custom cells. So let's say you just have a comparator that you manually designed. If you can create the cell view info of that manual design, which is just providing the library name, cell name, it won't have a Verilog A, of course, but it will have like the location of the ports. Then back can take that and run it through the measurement flow and the design loop. Well, it won't be a design loop, it will just be the measurement. But yeah, you can run measurements in Back 3 on custom designs. So yeah, if you want to learn only the measurement side of Back 3, like you can just become an expert in that without even learning in the layout at all. Or alternatively, you can also just learn the layout and then learn the measurement later. So yeah, it's like a really incremental kind of thing depending on how much you want to get into it.
It makes sense. Another question, somewhat related. Does everyone in BWRC use BAG?
No, not everyone. It's kind of mostly used in the in this like mixed signal like wireline design group, but that is also because like most of us are in Eladalon's group, and everyone in Eladalon's group works on Sardis, and we are also the developers of BAG, so we kind of optimize BAG to work for this mostly. But people in Vladimir's group have also developed another version, which is called the Berkeley Photonics generator, BPG, that can be used to design certain photonics devices that they use for their integrated photonic circuits. So they have been using it as well. People in Ali Niknej's group who work mostly on RF circuits, they haven't adopted back so much yet, but like there are definitely more RF features now than there existed before, because one of the main reasons they were not getting into it is because they needed to run electromagnetic simulations, which were not available before. But now that we are pushing speeds to 160 gigahertz or more in wireline, I did have to implement all this EM simulation stuff. And so now that this is available, hopefully the RF people will start using it as well. Then people in Professor Bora Nikolic group who also work across various different like ADC designs. So Zauka is from Professor Bora's group, and as you saw, he also uses BAG. So yeah, I mean, I would say there's like a 50-50 mix. Like there are a lot of people who have been using bag, maybe not all the features, like some particular features that suit their needs, and some others who still do manual design. So yeah, it would be like 50-50, I would say.
Makes sense. Thank you.
I have another question.
Mhm.
You mentioned that the primitives are published by Google, no? The Sky 130.
Mhm.
Is there
Yeah.
anybody who's using BAG on the MPWs to tape out?
Um, so
Then-
okay, so if you are asking questions specific to Skywater 130, the thing is I myself don't work in Skywater 130, so I don't know like the exact details for that. Yeah, I have been mostly working on FinFET processes for these high-speed designs. So yeah, maybe I am not the best person to answer about Sky
Okay.
130 development.
Can I step in just shortly? I think Bora was mentioning that they are preparing either SAR ADC or something like that to be taped out.
Yeah, I
Like
think that
what?
has actually, yeah,
Maybe
I think that has
Jacques or
already happened. Yeah,
Felicia
yeah.
or somebody else, I don't know.
Yes. So I do know that over the summer there was a Skywater 130 tape out, and Felicia took like some version of Zaopai's ADC, probably made some of her own feature additions as well, and did tape it out. So yeah, like I know that the tape out happened, but yeah, if you want more details, you should be talking to them.
Okay, so I can talk with Jokai in order to.
Yeah.
Yeah. Okay. Thanks.
I have one other question regarding the documentation. Do you have
Mhm.
already some concept for example, verification reports, generator documentation, or the generator documentation? Yeah.
So that is a good point. We haven't done a good job with documentation historically. One of the reasons for that is because like things keep changing so much that you write a documentation and 1 week later it's outdated. So what we end up doing is we do make very nice doc strings for our Python methods. So I think the easiest way to actually understand what a certain method does is you just open up the Python file and you read the doc string there. We do have a documentation generator which just parses through the Python files and puts all the doc strings in one like PDF or something. But yeah, I mean, in general, yeah, I mean, documentation is definitely a big problem, and yeah, so far it has kind of been like, yeah, documentation is just read the Python code. And I mean that's the best way to make sure that you are reading the latest up-to-date version of everything. But yeah, maybe in the future we will try to write up like more extensive documentation and try to make that available as well.
What about the verification reports?
Verification people?
Yeah, so when you run some simulation or some characterization, you probably want to view the results and save them. Do you have any concept for that one?
Not really. I mean, once again, given that like in the PhD setup, like it's the same person who's kind of doing everything. So like I did the simulations, and now when I test the chip that comes back after fabrication, like I will just load up the simulation results and try to match across that. So yeah, I mean, yeah, like I said, we haven't done a good job with documentation yet. So that's something that we definitely need to work on.
Anybody else?
Theo has a question. He's coming up.
Thanks.
Can you hear me?
Yeah, I can hear you.
Do you have experiences for failing over 1,000 simulations because you didn't start simulation from a proper initial point?
So I think I showed you like this example that Paul did, which had like 3,000 data points or 3,000 simulations. Sorry, like, can you maybe repeat the question? Maybe I didn't fully understand what you were asking.
Do you have experience for failing 20 hours simulations because you didn't start the simulation from proper one?
So I guess you're just talking about the initial seed, right? Yeah, like the way this happened is like usually the we try to limit the design space as much as possible based on physical constraints of area and whatever. And then here you can see that Paul came up with 3,000 data points, and then we can interpolate between the data points to generate other data points as well. And then like for the seeding thing, so that we rely on the Sci-Fi optimization to optimize there. And yeah, like I think so far in the use case that we have used it, we didn't really run into too many like converging to a wrong point kind of issue. Like I think he was able to start with some reasonable seed based on like some analytical analysis of the circuit. And yeah, by doing that and by having the 3,000 data points and also interpolating between them, he was able to come up with like a particular device sizing that satisfied everything, like all the performance metrics that he cared about.
Thanks. And the second one is regarding optimization. Have you been using machine learning techniques such as reinforcement learning or just looking your result and finding the optimal points?
Okay, so that is a great question. So we have been building up towards machine learning. I mean, this is kind of like the very like basic machine learning kind of happening over here, which is just Sci-Fi optimization. But we can do more dedicated things in the future. So another person from our from my cohort who's called Kurash, he had developed a certain framework called BagNet, which he had worked in Bag2 before. So it was using like designs generated by Bag2 and then doing a lot of genetic algorithm to come up with the final optimized design. We haven't made it work with Bag3 yet. So that is once again one of the new upcoming features in the wish list. But yeah, I mean, it should definitely be possible because I think we have like all the pieces in place. It's just a matter of someone actually putting it together. And then instead of this optimized to meet specs, instead of using Sci-Fi optimization, you try to put some kind of machine learning.
Do you have any examples of Bag3 being used outside of Berkeley, like outside of BWRC and Blue Cheetah?
No, I'm not sure if so. For first of all, so I don't work at Blue Cheetah anymore, and I think they have like rebranded their version of it. And so yeah, like legally speaking, they also don't really use Bactry. So we are now the main developers of it, and I don't I'm not sure if any other places have started adopting it yet.
But the thing is that since the open access is missing, nobody can adapt it even if they want to. No.
Yeah, that is definitely a problem. So, like, yeah, I mean, so yeah, that is one of the main reasons why I guess most other presses haven't been able to use it yet. So, yeah, we do need to. I mean, like, I don't know, like, what's the best solution for that.
So the thing is that even Jokai was an intern here at Intel, and he tried to install it, and it was not possible. So, and if there was you know, for Jokai not possible, there seems to be really a big hurdle. Are you not then afraid that people kind of go on Bag2 and develop it there, and then it's kind of splits into two different projects?
Yeah, I mean, so like once again, so that is actually a part of Bag which is like kind of beyond my understanding as well. Like getting that the way integration into Bag and then how to not have that. So I know that the reason we did that instead of doing the skill-based approach in Bag2 is because skill is like significantly slower. And so like even in like the later versions of Bag2, we had started switching over to OA instead. But yeah, I mean, of course, like you mentioned, this OA thing is definitely a big issue. So
You can
yeah,
still
like
go on You can still go on GDS based. You don't need to go on OA. And Bag2, that this GDS based generation is also enabled there. No.
so we do have GDS outputs. Like instead of creating OA layouts, so even in Bag3, you can generate GDS outputs as well. I think there are certain features that will still work without like Virtuoso at all. like even now, like if I want to do a certain like design loop, I don't even need to start Virtuoso. Like in back to one of the main things was you start a Virtuoso, you load startback.il into that. That is completely gone now. So we can work like completely independently of Virtuoso at the moment, but I think there are like certain OA functionalities that are still used in different places, but I will actually have to test that myself, but I think you will be able to generate things like directly to GDS as well, and then like open it up in K layout or something. But like I said, I think the main concern is compiling the C++. So we will have to split the C++ into the OA dependent and the OA independent part. And then if people just compile the independent part, then you should be able to use that without having the OA related features.
Yeah, I mean, it would be great for the open source community that they
Yeah.
can they actually be able to try it out.
Yeah. Yeah, maybe that is something that we will try to do. Like now that my tip out has finally almost wrapped up. Yeah, maybe that's something that I can look into.
Awesome.
So
Thanks.
on the OA one, so I guess would there be an option to release a compiled version? Is it just the source code of the OA, or are you restricted from releasing a compiled version of bag 3 even?
We can release a compiled version of Back 3. The problem with that is you won't be able to develop in C++ anymore. Like that. So what initially happened is we did get a compiled version from Blueshit as well, but then we realized there are so many bugs and additional features we want to do in the C++. And the moment you change C++, you have to compile it, and to compile it, you need OS. So yeah, like if you like it's the same problem. If you cannot compile it, then you cannot change C++, and then you are stuck with whatever bugs we currently have.
Yeah, you still have something, right? And then for a university, I mean, I guess maybe you weren't involved with this, but how easy is it to get OA access for a university or even a company? Do you have any thoughts?
Yeah, I wouldn't be able to advise on that. You would probably have to ask like our lab admins about that one.
Tejo, you wanted to ask some question. Is your question answered or?
Yeah, that's okay.
Okay, thanks. Anybody else? Okay, we need obviously to digest this whole presentation. Ayan, thank you so much. It was really interesting to see, what is happening behind the closed doors, or at least not behind the closed doors, but yeah, we can only check maybe the Git repo, but not actually execute it. A lot of things are going on. So my question for you is like, do you think that BWC is actually quite like secluded and isolated place where you have such a high concentration of people of different profiles that can help you out to make all these like changes so fast and be so fast onboarded? So do you think that this is possible to replicate somewhere else, maybe with back two, or in another sense, what do you think is the recipe for somewhere else pursuing programmatic IC design approach with back two, for instance, or
So I mean, I definitely think having more people is better, because so the developer team I was talking about is really just like 2, 3, like maybe 4 people at the most. And so like we often get and none of us are like experts in C++ yet either. So whenever we have to make a C++ change, it's kind of like figuring out first of all where I need to change it, and then a lot of going on Stack Overflow to understand how to change that, and then we finally end up doing it. So yeah, like the more people you have, things definitely become easier. Like if you have more, not only bag, but one second, this applies for any other generator based method you may have. But yeah, I mean, the more developers you have, the more users you have, you also get better documentation. I mean, that's another reason why we don't have documentation, because when you have only 3 people working on it who also have to design their own chips for their thesis, like we really don't have time to go back and write documentation for other people. So yeah, I mean, I think it is definitely going to be much easier to adopt this in a setting where you have more people involved in this project rather than like 2 or 3 people the way we are doing it over here.